All right, let's start. Seems like everyone's sleeping in today. Do you have any questions? Okay, so let's kind of start from where we left off last time. So what we were discussing last time was the idea that if we have hypothesis tests H0, theta equals theta naught, H1, theta equals to theta 1. And we have a critical region of size C, okay? Size alpha, region C of size alpha, okay? Then the power of C, right? The power of this test, or power of C, is exactly the probability that we are rejecting under the alternative, okay? So notice it's not probability of C complement, that's type 2 error, okay? This is the probability that we do the right thing under the right condition. So this is 1 minus beta. I mean, of course, there's this idea that what happens under the null, and of course under the null is fixed. So we don't discuss. I mean, you know, if you look at the definition of power, it's both under the null and under the alternative. But really, right, what we focus on is only what happens under the alternative, because alpha is fixed. So how do we know that C is the most powerful critical region? How can we know? That C is the most powerful? Now, of course, it's most powerful among its class. So in other words, it's the most powerful of size alpha, okay? Because of course, if you change alpha, then you have more room to change the beta, for example. So to have a fair comparison, right? I mean, if alpha increased, then beta decreased, for example. So to have fair comparison, we only compare critical regions of the same size. But among the critical regions of the same size, how do we know that, right? The one we come up with is the most powerful. So the example you want to keep in mind, right? And then from there, we can branch off to other examples, is the following: x1 up to xn, IID, normal, mu1. And we have the hypothesis test, let's say mu equal to 0, and let's say mu equals to 2, right? Or, I mean, well, let's try to be abstract, right? Mu naught, mu1, well, we know that mu1 is bigger than mu naught. And the critical region C of the form x bar bigger than or equal to k seems to be the most reasonable one that we can come up with. But on the other hand, how do we know, right, that this is the most powerful? In other words, are there other critical regions that we have not imagined that somehow may be more powerful than this one? Okay. So first of all, of course, it goes without saying that we choose K, right? We choose K. So that big K, right? So that probability, right, of C given H naught is equal to alpha. So we choose K, so that C has size alpha. So how do we know that C is the most powerful? Given that big K, right? How do we know that C is the most powerful? And so here, Neyman-Pearson lemma provides us with the answer. Okay. And so the setup of Neyman-Pearson lemma is exactly this. So the emphasis is it only works with simple hypothesis. And we'll comment on this. But basically, if you remember from our discussion of power function from last time, if the hypothesis composite, right? If you remember from last time, we have this power function, right? So this is like theta naught, and we can have a power function that looks like this, and another power function that looks like this, for example, right? So this is A and this is B, for example. Then if, let's say, theta 1 is over here, then A is more powerful, right? Of course, if you change the shape of B to be like this, for example, so this is the power function. If you change the shape of B to be like this, right? Then at theta 1, for example, in this picture, A is still more powerful. Yeah. What do you want to see? Any question? Okay. Right. So these are power functions, right? This is a probability of C, right? Given the hypothesis. Okay. So this is a power function. So sorry, probability of C given theta. So this is power function. So the point that Neyman-Pearson has to do with simple hypothesis is quite intuitive, because if we change this to a composite hypothesis like this, so if this is H1, right, then you see that at some point in H1, B is more powerful, but at some other points in H1, A is more powerful. Then there's no direct comparison between A and B, right? So Neyman-Pearson or not, we just cannot compare, right? Sometimes, right, with certain structure, we just cannot compare two different critical regions that are composite, if the hypothesis is composite. So that's the reason, okay? But anyway, so let's go back to Neyman-Pearson. It says that, right, if there is a K, and this is small k, okay? So that the likelihood ratio, okay, LR, likelihood ratio, which by definition is just the likelihood under the null divided by the likelihood under the alternative, okay? This likelihood ratio is less than that constant in C, and the same likelihood ratio is bigger than or equal to K, right, in C complement, then C is the most powerful. Now, again, most powerful of size alpha, okay? Because if two critical regions have different sizes, it's unfair to compare them. So it gets tiring, so I won't repeat that, okay? When I would just simply say most powerful, but most powerful among its class. All right, so the focus, right, of today's lecture, so goal, right, is of course, I mean, the simplest technical goal for you guys to master, right? I mean, for your exam and things like that, is how to apply Neyman-Pearson, okay? How to apply Neyman-Pearson. So we'll do examples, but conceptually, so that's one. Conceptually, the most important thing to get out of here is the concept of likelihood ratio, okay? Understanding likelihood ratio. And I guess, I mean, from my point of view, 2 is much more important than 1, okay? 1 is just a technical thing that after a few problems, you can get it. 2 is more important to understand, you know, the whole motivation of like doing what we do. So I will kind of approach 2 first and then go back to 1, okay? So 2. So first of all, right, what is the likelihood ratio? Well, right here. So remarks about likelihood ratio. So first of all, right, likelihood ratio, I think, let's say something obvious first. Likelihood ratio, right, is a function of the sample. So actually, it is a statistic, right? Anything that depends on the sample is a statistic. So likelihood ratio is a statistic. More importantly, actually, is a test statistic, okay? It is a, let me call it a universal test stat, specifically. So remember, a stat is just something that depends on sample, right? And then we attach some name to the stat. So to talk about its function, like an estimator, right, is a stat that uses to estimate, that is used to estimate parameters. A pivot stat, right, is a stat that is used to construct confidence interval. A test stat is a stat that is used to accept or reject, right, the null hypothesis. So likelihood ratio here is a stat that exactly can be used, or is a universal, right? I'll explain what universal means here, to reject or accept the null hypothesis. In other words, right, we have to go through the technical details, but by forming the likelihood ratio, we can use that as a sensible criterion to accept or reject any kind of hypothesis test that we can come up with, right? That sounds pretty impressive, but that's just the case. So, and that's what I mean by the word universal, right? Any kind of hypothesis test, likelihood ratio can be an approach for it, right? May not be the best, okay? May not be the best, but can be a sensible approach. The same thing with, you know, method moment or maximum likelihood estimators, right? Any problem, any estimators, you can apply the method moment, but the method moments and likelihood ratio, maximum likelihood on it, right? Whether in those specific problems, right, the estimators you come up with are the best estimators is a different question, but the sensible approach is always there. So, all right, so let me just give you an example. And actually, I mean, there's not much example to give. We'll look at that later. But the reason why it's a universal test stat is because of its construction, right? The idea is you want to reject the null if likelihood ratio is small, and then accept otherwise. That's it, right? Why is that the case? Because you see, as I mentioned last time, right, likelihood ratio is very intuitive. It weigh the evidence, okay? It weigh the evidence of seeing your sample, right? I mean, if you are into, you know, I don't know, CSI, that kind of things, then the sample is your evidence, right? It's your crime scene evidence, okay? The criminal is exactly the unknown hypothesis. Okay, so you see the evidence, right? You weigh the evidence under, right, these two scenarios, and obviously you go with the one that gives you the more plausible evidence. And so if this ratio is small, that means that the evidence under the alternative, right, is higher than the evidence under the null, so you reject the null, and then you do the opposite. All right. Now, Okay, any question on this? So here, right, let me pause and then give you a demonstration, okay, on the code to show you how likelihood ratio works. So here, I generate, this is like flipping a coin, okay? This is like flipping a coin. I flip a coin 10 times, and I have two scenarios. Either my coin is fair, or my coin is not fair, it's biased. And here I take the, I guess, or if you think of one as a head, then it's biased toward, you know, the head, okay? So, and then I flip it 10 times, and I see, right, the evidence. Now I think, right, try to think of this question is very intuitive. If you see, right, if you flip a coin 10 times and you see this evidence, and someone asks you, well, do you think, right, based on this evidence, is a coin fair or not? All right. Now, I'm not trying to say that, right, this is the only way to approach it, right? We can obviously approach it through the estimator, right, direction. But one way is to weigh the likelihood, right, of seeing this sample under the norm versus, right, the likelihood of seeing this ratio under the alternative. What's the likelihood ratio? Sorry, what's the likelihood? Right here, right? This is exactly the likelihood. P naught, right, raised to the 1 or 0 times 1 minus P naught, right, raised to the possibility of not seeing it. Because if it's 1, then you multiply with P naught. If it's 0, you multiply 1 minus P naught, okay? And so here, right, in this particular instance, you see that the sample is generated, right, under the true hypothesis, I mean, under the hypothesis that the coin is fair. And so you see that the likelihood ratio, right, the likelihood under the norm is higher, right, and likelihood ratio is like this. And by the way, right, where do I set to, what threshold do I set to reject or accept? You know, like there is this mysterious little k where I say if the likelihood ratio is small, right, we reject the norm. But how small is small? Okay, we'll get there. But for now, in this simulation, I just set that to be 1. So if the likelihood ratio is less than 1, I go with the alternative. If it's bigger than 1, right? If it's 1 or bigger, I go with the no. All right. So let's run it a couple of times to show you. Again, right? So here you see, actually here is kind of interesting, right? You have 7. Oh yeah. Okay. Actually, it's the opposite now, right? You see here, the no is still true, right? The no hypothesis is still true. But of course, by chance, right? Even if with a fair coin, you can have more 1s and 0s, right? You can have, by chance, with a fair coin, you can have more 1s and 0s. Now you see, here we make an error, right? But the evidence with 7 1s, right? 7 heads, it points to the alternative to be true, right? So here we make an error, right? What type of error is this? Type 1 or type 2? What kind of error are we making? Yep, type 1, right? We're making type 1 error. Now, but let's run again, right? You see, the no is more likely to be true because likelihood ratio, right, is bigger than 1. So, right, you see, because the true sample, right, the true P is 0.5, most of the times, right, the likelihood ratio test, right, the likelihood ratio should provide me with the right answer. But once in a while, right, I will make one of the errors. But here, because I know that this is true, I can't make type 1 error. Let's change it to the opposite direction, right? Let's now say the true mean, right, the true proportion, right, is 0.7. So here, right, you see, somehow, even though 0.7, the coin is biased, we still get less heads, right, than half of it. In this case, the evidence points to the no, more likely to be true. All right. So here we make type 2 error. So again, likelihood ratio just gives you a sensible way to do so, right? So here, likelihood ratio is less than 1. But that doesn't mean, right, it is foolproof or anything like that. It's just a way. And you see, most of the times it's pretty okay, right? You just weigh the likelihood ratio. Any question on this? All right. So maybe one last question before we go back to the lecture. What's going on with this little k? Like, do I have to choose it to be 1? Can I change it? And if I change it, what am I playing with? Right? So right now I'm setting k to be 1, right? In other words, if the likelihood ratio is less than 1, then I go with the alternative. If it's bigger than or equal to 1, I go with a no. But why 1, right? Is arbitrary, right? Why not 0.5? Why not 2? So can I change it? And if I change it, what am I doing? So let's see, right? If I change k to 2, what do you think will happen? Suppose that right here, right? Let's say the no, right? Yep, those are very good questions, Alice. So yes, I mean, you can say absolutely, right? Because of course, this is my rejection accept region, so I would change the critical region. But I guess more directly, what am I changing? Yes, I was thinking I'm playing around with alpha, right? I'm changing around with alpha and also indirectly beta, right? By changing the k, exactly, I'm playing around with the alpha, right? It's just how tight you want the alpha to be, right? And so if I think, right, because, okay, let me answer Alice, right, question. Does it have any dependence on n? Absolutely, right? Because why? Here, you go through, I mean, the likelihood function is the product, right, over the whole, over a whole sample, and it has a direct tie to n, right? And actually, you see, in terms of, I don't know, I want to use the word power, but I'm not sure it has the same meaning as the power that we've been talking so far. But obviously, the more sample you have, the more information you have, right? The more likelihood ratio approach the true information, whatever that means, right? So the likelihood ratio definitely have a direct dependence on that, right? And we have to carefully word this, but roughly speaking, the larger the n, the more the likelihood ratio will point to the right direction for you, right? I mean, that statement is very vague. I have to really qualify it. Okay, does that answer your question? Yeah. So what is it, right? So for example, if I change k to be 2 here, right, and the null hypothesis is true, do I increase my alpha or decrease my alpha? Can you see? If I change k to be 2, right, do I increase or decrease my alpha? So before it was 1, right? Now I change k to be 2. Do I increase or decrease my alpha? I decrease my alpha. All right. So let me ask this, right? Am I more likely to reject or less likely to reject? So k right now is bigger. So am I less likely to reject or more likely to reject? I'm more likely to reject, exactly. If I'm more likely to reject, right? Then am I, so then I'm more likely to say that the alternative is true, right? Then probability of C given the, right? Actually now, let's use Alice's observation that now I increase my C, right? I increase my rejection region. So therefore, I think I'm going to increase my alpha. Is that okay? I think that's the case. Do we agree? So Danny is right. Is it okay? Yeah, right. I mean, it's very simple because here, right, really, this is my rejection region. So Alice actually has a point too, right? This is a very good observation. If I increase K, I increase my rejection region. Do you agree? So therefore, right, my alpha would increase. So actually, if you want to make your alpha stricter, you got to make the K smaller, right? But here, the whole spirit of the likelihood ratio is just weighing evidence. Where you want to make the cutoff is exactly how you want your alpha and beta to be. Is that okay? That's all I want to point out. And then, of course, right, once you understand the spirit, you have to go back to a table and make the precise calculation to see, where the cutoff should be. Is that okay? All right, cool. So let's go back to, now I don't see my chat. Hold on. Give me a moment here. All right. So that's A, right? Oh, I need to share a screen with you. Okay. So now, so that's A, okay? So I hope I demonstrate A for you. And then you see, right? So that demonstration was for a proportion. You see this for the mean, for the variance is the same thing, right? Because likelihood is how likely you see that under the hypothesis. It doesn't care what kind of hypothesis you're talking about, right? It's the evidence overall, right? You think about likelihood function, the likelihood, right, of the sample gives you the how likely you see the sample, right? So it doesn't care what hypothesis you put in there, as long as you can do the calculation. You can calculate the likelihood given your hypothesis. All right, but now B, right? The next observation is this, that usually, okay, usually the task, and this depends on who you talk to. You don't have to do it. Maybe you have to do it. The task is to simplify the likelihood ratio, right, which is a stat already, to a dependence on another more intuitive test stat. Okay, so in other words, you try to do something like this. So this T of X is the test stat you want to use. Okay. What does that mean? Let me point out. Let me show. Let me give you a big picture. All right, and then we'll. But basically, this is exactly the connection between this. By the way, right, this relation right here is exactly the connection of Neyman-Pearson with whatever you want to prove. I mean, your critical region. For example, right? Suppose you have that x1 up to xn, IID, normal mean mu, variance 1. And suppose that the null is that mu equals to mu naught. The alternative is mu equals to mu1 bigger than mu naught. Okay. So your critical region, right, is sorry, x bar, right, bigger than equal to k. Now, so here, x bar is exactly that intuitive test that I'm talking about. Okay, X bar is that intuitive test step. Why? Why is it intuitive? Because someone who are experienced with estimator would say, well, you're estimating, you're talking about, right, the population mean, your test about the population mean. So obviously, right, to make any statement about the population mean, you use a sample mean, which is its estimator. And because mu1 is bigger than mu0, you would reject if the sample mean being representative of the population mean is high enough. All right, so that statement is very intuitive. On the other hand, right, Neyman Pearson, likelihood ratio would say, well, I would reject the null if the likelihood ratio, which is, right, by the way, I'm just going to write it. So to remind you, which is the likelihood ratio, right, is small enough, right? So the point is, these two regions are equivalent. And that actually is most of the proof of Neyman Pearson. It's just to establish the equivalency of C2 and C1. So in fact, even though you write C1 and C2, they're really the same C. Is that okay? Right? You see, we will do the example again, right? But the point is, right, the likelihood ratio here, when you do all the algebra, all the arithmetic, something else will pop out, like X bar, for example, and you're like, this less than or equal to K means X bar is bigger than or equal to K, big K. Therefore, right, I mean, intuitively, let's just use this. Is that okay? And then so in fact, right, to prove this is the most powerful, the task is to establish the equivalency of, likelihood ratio rejection with your proposed rejection using the intuitive step. All right. Now, why do I say this is not necessary? If your goal, right, is to accept or reject, then you don't care if you use this or you use that, right? As long as you have a robust, right, alpha and beta. So whichever test that you use, in fact, may be, irrelevant. But people, of course, traditionally prefer this format because somehow, right, it speaks directly to the fact that you're talking about the population mean. Are we okay with this? We'll do example, right? I mean, for sure. I'm just walking through the big picture here. Another example exactly is the simulation we talked about just recently. So suppose that these are IID Bernoulli P, right? The null is P equals to 0.5. Your alternative is P equals to 0.7. Now, tell me, what is the intuitive rejection region here? What is C? That would be intuitive. Correct, or p hat, not 0.7 Alice, K. Actually, that cutoff, right, doesn't have to be 0.7. It really depends on alpha. So yeah, p hat bigger than big K or X bar bigger than big K, because X bar or p hat is just a notation for the same thing. Exactly, right? This is the intuitive rejection region. On the other hand, right, on the simulation, what did I do? On the simulation, I did exactly the opposite, right? I mean, not the opposite, I did the other one. Like the ratio less than or equal to K. All right. The task, right? Now, admittedly, right, sometimes this may be different rejection regions, who knows? But the task, right, if you want to establish this is what most powerful is to establish that they are equivalent. Equivalent. Okay, they are one and the same regions. Question here. last example, x1 up to xn, but let's switch gear, right? Let's do normal 0 sigma square. So now the unknown parameter is sigma square. So let's say the null is sigma square equals to, let's say 1. The alternative, sigma square equals to 4, let's say. All right, let's change flavor. Let's do 4 and 1. All right, what is the intuitive critical region here? What is the intuitive critical region? Yeah, big K, right? I hope, I mean, you see, the symbol starts to get annoying, but you just want to be consistent. No, don't worry about it. I'm just trying to point out so you will keep your notation consistent. The big K is reserved for the parameter and small k is reserved for the likelihood ratio. You know, so we can distinguish the two. They are really related, right? But yeah. So C1, right, is S squared less than big K, exactly like with offset. And guess what the C2 is? C2 is still, does that surprise you that they're all the same? Even though I switch direction here, even though I switch sigma square here, I switch the relation. Like, suppose if I change it like this, right? What changed? What changed here? The C2 changed. The C1 changed. Correct. Only C1 changed. C2 does not change. Okay. That is exactly why I say it's a universal test step. You always reject when it's small. It's that simple, right? But of course, you know, because of the relation and how the things play out, right? This same region may correspond to different, right? C1, depending on how the, you know, these numbers play out. Let's do this. So again, right, equivalent. Are you okay? So now, maybe let's ask the last question, maybe, I don't know. So as I pointed out, right, the name of the game is to simplify the likelihood ratio to a more intuitive stat like this, right? So there are many reasons why we do, you know, the work we do, sometimes to make things more aesthetically pleasing, right? You know, turn into something we're used to. For example, I would argue, I would completely agree that somehow this is more aesthetically pleasing than that. But of course, you know, if you start to understand likelihood ratio, you see, yeah, there's not really much difference. They're intuitively, yeah, it's so confusing. I don't know which one I used. You mean this one or the other one? This one? So like this, right? This setup? Yeah, sure. Argue it out for yourself, right? What does C mean? C means rejection, right? C means rejection. So, okay, look at these two hypotheses. When do you reject? Do you reject when the sample variance is large, or you reject when the sample variance is small? I mean, look at this, right? When do you reject? Right? Is small, I think, right, is obviously captured by this. Is that okay? Yeah. All right, so all right, then Danny, right? Exactly, that's why I asked, right? So the point is, right? That's why I asked this question. If I switch this, what changed, right? And I think John, right, said it correctly. What changed is only this and not that. So first of all, right, let me say this, that if, as we do more, some more concrete examples, I will point out to you, in the detail of the calculations. But I want you to see at the big picture too. This makes sense, right? So if I switch like this, I only see one switched. Why? Because, as Madhav was asking, right? What does this mean, right? Well, here, looking at this, I would argue, right, that I would reject when the sample variance is large, right? I mean, clearly that's what it says. So here, that's why C1 changed like this. Why does C2 not switch? I think that's more like your question, right? Not like sometimes a different sign, different. Why does C2 never switch sign? Okay, can Danny or anyone answer that question? Why does C2 never switch sign? Or in other words, right, that's exactly what. You understand or no? I still have a question, right? Why does C2 never switch sign? That's why I say it's universal, right? Why does it never switch sign? I mean, so more appropriately, the observation is, you see here, I never change C2. Why? Yeah, but what, fine. That justifies the name universal, but that still does not explain why, right? Why is it universal then? What is it behind its construction? What is it behind its meaning that makes it universal? Meaning what that makes it structure like this? So again, right, this has to do with its meaning. What is likelihood ratio? Likelihood ratio is weighing the evidence between the null and the alternative. It's always that way. I mean, if you somehow switch the definition like this, then obviously it will get switched. But no, right? Convention always say likelihood ratio is the null over the alternative. All right, that's the only place where convention comes in. But if you accept that this is the way you write likelihood ratio, then you will never reject when it's large. Why? Because weighing the evidence, right, of the null against the alternative, if it's small, that means the evidence under the null is less than the evidence under the alternative. Hence, you reject. Is that okay? You only reject when the evidence under the null is less than the evidence under the alternative. That's why it's universal, because of its construction, because of its meaning, right? Because it's weighing, yeah, it's weighing evidence, right? Again, both of these. Again, like I don't want to repeat myself, but this is why stat is hard. It's hard not because, well, the probability, whatever, that's the technical side, right? A lot of times as students, you approach it very formulaically, right? You look at the ratio, you're like, okay, what can I do with it? The meaning, right? What is the meaning? Once you see the meaning, you'll see why the pattern is always that way and never any other way. It is quite intuitive. All right. Yeah, well, good question. So let me keep it like this, right? Let me not switch it too many times. All right, so I guess back to my question. My question was, right, so the transformation, what's the point? So one point is to make it more aesthetically pleasing. Fine. Do you see any other practical reason that we want to, work with C1 rather than C2? Practical reason, not, aesthetic reason. Sure, Christine, I would agree, right? That's why I was saying, like, C1 is more intuitive. But like I said, right, I mean, suppose that your boss knows sample mean but doesn't know likelihood ratio, then you would do as I did, right? You would go say, boss, look, all I'm doing is weighing the evidence, right, of the null versus the alternative, and then I just reject when the evidence is less. I think, right, your boss, being hopefully an intelligent person, would understand this. So understanding is fine, but so that probably is not the, like strong reason why you probably want to work with C1. Any other reasons stronger than understanding and intuition? Technical reason even, right? Absolutely, Alice. That's exactly it. Exactly. Right. Notice that once you come up with C1, C2, that's not the end of the story, right? The end is the story then is what level, what specific level are we going to go with? All right. And then at that time, you have to get your hands dirty and start to calculate probability under the null and under alternative. And exactly, right, the sampling distribution of the stat, of the, the traditional stat that we used to know, we have worked on so hard, right, from chapter 8 and etc., is known. This is normal, etc., right? This is chi-square, etc. But the likelihood ratio, right, before you simplify it, you don't know what that is, right? It's just a likelihood ratio, the sampling distribution, right? So the sampling distribution of the likelihood ratio might not be easy to derive in general. That's it. That's exactly the practical reason, right? Because I mean, right, because the reason, right, is we need to decide this concrete, right, value of little k or big K, right, corresponding to alpha. All right. Now I say might not be, because if it turns out that these two are equivalent, then the probability of this is the probability of this, so you do know it. All right. But in general, as you'll see, right, the whole I don't want to say issue, right, but likelihood ratio is very universal. But when it comes to knowing the distribution, so you can draw the line of rejection, sometimes, like, it's unclear what that is, and that's where you want to do the work to hopefully transform it to something we know. Are we okay? Any question before we now start to do calculation examples? All right, so so maybe one last remark, right, about Neyman Pearson. So basically, right, Neyman Pearson tells you this. Neyman Pearson tells you that find show that with your critical region, right, likelihood ratio less than or equal to k like this, and we can look at like in C bar. And so let me say this, the crux move of Neyman Pearson. And this, I say this because students tend to feel confused about Neyman Pearson. They don't understand what it's asking them to do, and they don't understand even when it's done, right? Why is it done? So the crux move of Neyman Pearson is this, right? So the point is, for example, let's take an easy one, right? let's say that the example is x1 up to xn, IID, normal mu1. And you want to show, right? So, sorry, the null is mu equals to mu naught. The alternative is mu equals to mu1. You want to show that C, right, equals to x bar bigger or equal to k is most powerful. So you go and you try to invoke Neyman-Pearson. Neyman-Pearson tells you this. Look, right? Whoops. Neyman-Pearson tells you this. Look, try to somehow, right, draw the equivalence between this and this. That's what Neyman-Pearson tells you, right? So, but the crux move is this. So, like I said, right, it ends up in this problem, for example, you'll end up that your likelihood ratio will be a function of x bar. Okay, in this particular example, your likelihood ratio will end up being as a function of x bar. So your task actually, right, first of all, is somehow to see that the x bar shows up in your likelihood ratio after your simplification. That's the first task. That's the first signpost. One to show. What the S maybe? One to show. Yeah, one to show. All right, that's the goal, right? Goal. Maybe goal, right? And so Neyman-Pearson, right, asks you to establish the equivalency between this and this, meaning, first of all, that make the x bar show up. So first step, right? Okay, because that's how the intuitive stat will show up in your likelihood ratio. Second step, right? Now that you have this, then now look into this, right? How can this and this be equivalent? Well, I mean, a student in analysis, right, will know this, because this is a function of this. You're saying, right, so now just forget x bar as a statistic, just think of it as a variable. You say that there's a variable that if it's high, then its function is low. Conversely, right, if this function is low, then this variable is high. Well, when does that happen? Answer, when this function is a decreasing function of that variable. So that's the crux move. I mean, I guess there are two crux moves. The first is to make sure that your stats show up, right? Your test stats show up. I mean, the intuitive stat, because if it doesn't show up, then how do you make the link? So first make it show up. But after you make it show up, then just verify that the relationship holds, and that's it. So the crux move is to show that LR is a monotone function of T of X, whatever that is, right? For example, the crux move here is to show that LR is a monotone function of S squared. LR is a monotone function of P hat. LR is a monotone function of X bar. Now, why do I say monotone and I don't say anything else? Because whether it's decreasing or increasing depends on how the hypothesis gets set up. All right, so if you swap, it will be decreasing. You swap the other way, it will be increasing. Any question on this? This is the big picture that you want to keep in mind when you do Neyman-Pearson. By the way, right, the explanation for this one is this following picture. I think I draw it last time. Right? Think of it like this. So here's your X bar if you want. This is your likelihood ratio depending on X bar. So you see, right? This is your level K. And exactly this is your little k. And you see, right? Your X bar bigger than K is exactly when your likelihood ratio is less than little k. Are we okay? Any question? All right, so here, right, the general idea is to make Tx show up, right? Whatever Tx is, whatever the test stat that you want to desire show up is. So let's go over the example that we mentioned and show the concrete calculations. So, right, again, x1, xn, iid, normal mu1, h0, mu equals to mu naught, h1, mu equals to mu1. Mu1 is bigger than mu naught. Okay, question. Show that C bar, X bar, we can go to K. Is the most powerful. All right, so you see how your steps will go. First one, form your likelihood ratio. So likelihood ratio, right, will be, and here it probably is helpful to do some mental arithmetic or be used to likelihood ratio, so you don't have to write down a lot of things. But I know, right, that it's going to be a product of 1/2 square root 2 pi, that kind of thing. But because it has same variance, that they don't show up, it will just going to be this eta minus sum of xi minus mu naught square over 2. So let me do the 1/2 out here. And then eta minus 1/2 sum of xi minus mu1 square. Like that. Okay. And again, right, because I mean, if you don't organize your symbols, I mean, things can get a little bit tedious, just keeping track of things that don't have anything to do with anything, right? So this is this. We're okay. Second step, right, is to make sure that the X bar show up in this expression, right? So, or, the second step would be just simplify this, work with this. But I guess if you simplify blindly, maybe you won't get anything, right? Simplify with the goal that X bar shows up, because this guy is universal, whether your hypothesis is going to be on mu or on S squared, whatever, right? So you want to know your goal. Your goal is to make X bar show up. All right. Well, but notice, right, because of the exponential structure, the only guy that will play a role is this one. Yes. Because of the exponential structure, this is the only thing that you need to work on. Is that okay? So, and again, right, I know that I want X bar to show up here. So that will be n, right? Cancellation. Let's factor out the -2. I got mu1 minus mu naught. And exactly, right? Because I know that that's what I want. That's nx bar. Are we okay with this? All right. So now, right, then here comes some extra magic trick. And I mean, if you don't know what I'm doing, then that's exactly magic trick. But if you know what I'm doing, you see it's fine. What's the goal? The goal is somehow to establish the functional relation between LR and X bar. If X bar is here, do I care for this term? Do I care for this term? I don't, because, you know, in terms of functional relation, it doesn't add or subtract from the X bar, right? This is the, you know, MVP here, right? The most valuable player, or whatever. This is the guy that you want to focus on. The rest, decorations. So I would do this. It will be constant e to the minus 2 mu1 minus mu naught times nx bar. That's it. So you see, that's the task. So that is exactly the point of establishing the functional relation between LR and X bar. Any question here?
Could you repeat that one more time?
So I assume you mean this. So, right, I hope that you understand the goal, right, is to establish, because this is my rejection region, right? I want to connect it with LR, likelihood ratio. So anything that does not depend on X bar or is unrelated to X bar, I can cast it away as a constant. Because, right, the goal is to analyze the functional relation between likelihood ratio and X bar, right? To draw the connection between this and this. Is that okay? Still unclear, or I do understand that this is where, you know, you know what? That's just a typo. No reason. Sorry. No reason. No reason. Wait, hold on. Oh, you know, sorry, not here, right? Here. Yeah, I make a typo. I think there's an end or something. Is that what you're asking? Or maybe there's an end. Yeah. Oh, yeah, of course. You point out the end. Yeah, sorry. Thank you. Thank you, Danny. Yeah, I was too excited. But you see, like, yeah, the math is wrong. I admit. But you see, it doesn't hurt anything because, again, this term doesn't mean anything. That's why I guess I was careless about it, right? But this doesn't mean anything, right? Because, again, it's not attached to X bar. But yeah, you're right. I made a mistake. Yeah. Well, okay. So again, right, I do know that you, how to say this, right? This is why professors seem mysterious to you. They seem to be kind of oblivious to a bunch of things and they still get the right result. The reason is exactly that, right? You know, if you pay attention to too many details, you may get tired and you don't know what the main point is. You may lose track of the main point. I do the opposite, but that I'm not saying that I'm wrong, I'm right, except that, you know, like, this term doesn't deserve my attention. That's it, you know, only this, right? That's I hope you see that and you start to zoom in on that count. All right. We're good. All right. So now, right now, you see, this is it. This tells me all I need to know, because actually now I don't even have to look at the hypothesis, right? Tell me this: if mu1 is bigger than mu naught. Correct, exactly. It takes care of the other term. By the way, right, in case you are so anxious, if you write this on the exam, e to the something, I'm fine. I mean, right is right, all right? But I hope that you kind of relax more and then, you know, take a more kind of broad approach. It can only help your problem solving, okay? If you pay attention to too much details, The wrong details, by the way, right? You have to pay attention to the right details, but the wrong details is just going to hurt your problem solving. Okay. All right. So if mu1 is bigger than mu0, okay, if mu1 is bigger than mu0, then what kind of functional relation do I have here? LR of x bar. What kind of relation? So let me say this, right? What translation do I have? And if mu1 is less than mu0, what sign do I have here? Bigger or less? Which one do I have here? Bigger, exactly, right? What's the clue? The clue is if this is bigger, this is positive, this is negative. So it's a decreasing function. If it's a decreasing function, right, the sign flips. And right, like this. Are we okay? But do you see that, right? So here, if the alternative mu1 is bigger than mu0, the rejection region, right, the most powerful one is this. If the alternative mu1 is less than mu0, the most powerful one is this. By the way, I think this is your midterm 2 exam, right? But it doesn't matter. You see, this one single relation takes care of the whole thing. The rest are just algebra, whatever. And that's why I say it's universal. And that's why also this answers Danny's question, right? Why the signs sometimes flip. It's just because of that relation. You have to tell me how these are connected, and I'll tell you how that gets translated. Any question? I mean, so for once, right? I mean, if this was the particular question, then I guess you don't have to do this case, right? Because this is the question. But I mean, I'm explaining to you, so it doesn't really matter. Are we okay? Any point that you don't understand? Okay, so let's do the Bernoulli's example, right? The simulation example. So suppose I have x1 up to xn, IID, Bernoulli P, right? So let's make it a little bit more abstract, right? So the null is P equals to P naught. The alternative is P equals to P1, right? And exactly P1 is bigger than P naught, right? Was the example I did. But again, right, you see this one now, this relation is flexible, but let's just assume that's the case. Then show, right, that what? X bar. You know what? Let's just change the game a little bit, right? It's fine. X bar is bigger than K, right? Is the most powerful. Okay. So how do I do it? Again, right? Step one, likelihood ratio. These are Bernoulli's, right? So Bernoulli's, so maybe let me take it slow, right, and show you. So likelihood function is always product, right? Product over each individual. So each individual, right, will be this. Are you okay with this? So now, right, I would do that into P naught I mean, I'll write like this. I don't know if this is the structure I want. Right? No. This is where actually it might matter a little bit. This is n, right? Are we okay? All right. To simplify, I don't know. I think I did simplification here already. What's the goal here? What's the goal here? I want to make sure what shows up. Yes, right. You see X bar show, but do you see X bar already there? It's already there, right? Because this is just right. So I think that's easy. That's probably easy. What's the hard part? The hard part is to show that so in this case is equivalent to X bar bigger than or equal to K when P1 is bigger than P0. Okay. And let me emphasize, right? This is where I guess you can cheat if you know what's going on, but I'll be on the watch for this a little bit, all right? If it's obvious, I'll agree with it, but if it's not obvious, I'll ask for some more work. For example, right? Suppose this is, this is what you want to show. Then what's a magic statement? What do you want to show here? What do you want to say about this function? What do you want to say about this function? Decreasing, exactly, right? So is LR X bar is decreasing. This is where I say you can cheat because you say obviously, obviously it's decreasing, right? And this is where I say I'll be on the watch for this. I mean, this is right. I don't know. It's not that obvious to me, okay, that this is decreasing. But hopefully for the more honest student, knowing this shows you where to look, all right? This is obvious because there's only one single X bar here. I feel this is not as obvious, but fine. Do you see that this is decreasing in X bar? And how would you do so? Is it decreasing in X bar? Is it obvious? Let's, look at piece by piece. Is this decreasing in X bar? Yes, right, because P1 bigger than P0. So P0 over P1 is less than 1, right? Something less than 1 raised to it is decreasing. Great. So what's left for us to do? This. But here is where, the focus is important. Can you simplify this to something simpler? There's something that is not relevant, right? What is it? That should be, exactly. Now, you know what you're looking for, then yeah, but do you see it? The n would not be relevant, right? So the relevant, so right, to make it is decreasing, right? In X bar because P0 over P1 is less than 1. Then the other piece, right? What's relevant? The only relevant piece is this. Agree? So this right here is irrelevant. Is this decreasing in X bar? Yes, right. Why? Because now this ratio is bigger than 1, but you have a minus sign here. You have a minus sign here, right? So I guess you can say something like this. 1 minus P1 over 1 minus P naught is less than 1. There you have it. Are we okay? Any question? So I said I would be looking for something extra. That's something like this, right? I would say that, right? I mean, if you want to cheat, go ahead. If you say something this, say this much, I think you definitely get partial credit, right? Because I know you know what's going on. But right, if you want to be honestly showing everything, then something like this should be there, right? But of course, if something is obvious like this, then no need to show. Any question? All right, so let's hopefully quickly do one last example. But now, right, the table will be turned onto the sample variance. So now I suppose, right, the mean is known. H naught sigma square equals to sigma 0. H1 sigma square equals to sigma 1 square. Supposingly now, let's say sigma 1 square is less than sigma naught square. I want to show that S squared, right, is less than K, right, is the most powerful. Is it okay? Now, so step 1, likelihood ratio. So likelihood ratio, right, notice is almost the same, except now I have sigma square. Sorry, right, this is sigma 0 square, sigma 1 square. I have something else too, actually, but I will do as constant in front. So the reason, right, is this. The constant C, right, is 1 over 2 pi sigma 0 square raised to n over 2 divided by 1 over 2 pi sigma 1 square raised to n over 2, right? In the previous case, right here, the two multiplication constant cancel because they have the same variance. Okay. Here they don't cancel because, right, exactly, we assume they have different variances. But either way, right, this does not play any role in analyzing the connection between the likelihood ratio and the sample. So I just put as constant, but I kind of highlight it for you so you see it. All right, I realize time is up, right? So let me just write down step 2 and then we won't do it. We'll pick it up on Friday. So what's the name of the game? The name of the game is somehow to work on this expression. And show what? Somehow the sample variance show up, right, in this expression. You see, right? It could get pretty interesting and hairy, right? How does that turn into sample variance? But it must, because otherwise, right, our region being the most powerful cannot be right. So either we can do this and this is right, which seems intuitive, or right, this is wrong. I would want to bet that, right, that this can be done, but right, the road there may not be that obvious. Okay, so I think I went over time. Apologize. Let's stop here and let's begin on Friday. Yeah, you too. If you have any questions, I'll answer. If not, then see you. You too.